Video 5 of 10, halfway there to accountability, people. We're going to make it. It's going to be all right. In this video, we're going to talk about various properties of functions. We've talked about relations. We've talked about properties of relations. We've talked about how relations can be interpreted as functions. Okay, so now we're able to talk about some particular properties of functions. Okay, great. So I want to talk about a couple of concrete functions in this example. So let's do it. So I'm going to write the functions down first. So SQ is a function from reals to reals. SQ of x is just x squared. Okay, hopefully familiar. The function suck is a function nats to nats. Suck n is just n plus 1. Right, so this is just the S constructor. Okay, so there's that function. Pred okay, is the same one that we know from cock. Oh, wow. Terrible handwriting. Okay. Okay, one last one. This one's kind of funny. I'm going to call it swap. Also in the naturals. And then what it's going to do is it's going to swap evens and odds. Okay, if you're having trouble with that function, I really, really recommend you try running it on yourself. On some examples yourself. Hard to run it on yourself unless you're of type nat, which I doubt you are. Maybe some folks from Washington, D.C. So these four functions are going to be the primary way that I explain the concepts we need to know about these functions. Okay, so these are our core examples. Right, great. Okay, so there are a number of topics I want to describe. First, the parts of a function. Domain and codomain. And then the pre-image, and then the image or range. Okay. So for all of these functions, you can envision basically there being two sets. You gonna line up with for me? Anyway, great. Right, so we'll have some set A and some set B, and the idea is that, look, function f transports things from F to B. Right, this is the general picture people draw about these. Okay, so simply if that's f, right, so if we have f is a function from A to B, i.e. f is in this type and is deterministic, then we say that A is the domain and B is the codomain. People sometimes call the codomain the range. I find this to be very confusing because I think of that as something else. So inside A, there's a bunch of elements. Right? And if f is as a function should map each one of these to some elements over here. Right? So what we'll have then is what f does right, depending on the structure of f, no, excuse me. We might get different things. So we would hope that everything in f has a definition. So you'll notice that not everything in y, some things are lonely. unmapped. So what I'm going to do, this bit highlighted in pink, that's called the range or image of f. So that's the part of B that actually gets hit by f as a function, right? So these two other bits of y are not in the range of f, the ones that are circled in purple there, right? Now the pre-image, this is the pre-image of f. Right, now in this case, the f that I've drawn, everything in A has a corresponding mapping in B. That is to say, this f is total. So f is total, or is a total function when, and there's a bunch of different ways we can say this. So one way we can say this is pre-image of f equals the domain of f. Another way we can say this is more formally in math is for all A and A, there exists a B, f of A equals B. That's another way of saying it's total. Right, that's the property of a functional relation to say that it's total. Okay, so what have we seen? We've seen domain, codomain, image, and range, pre-image, and then total. F is partial, or is a partial function when when the image of f, excuse me, no, when the pre-image of f is a proper subset not equal to the domain. Right? Or when it's non-total. Right? It's just the negation of that property, i.e., there exists an A such that there does not exist a B, f of A equals B. There's something left undefined. Okay, so let's look at these functions we have up here and think a bit about the properties that they have. Let's go aren't. Haven't used that yet. Okay, square. So the domain, right? The domains are all of this, right? All of these are the domains. And then here are the ranges. So what is the image of the squares in the reals? Well, only positive numbers. So, oops. So we'd write something like R, not just positive, R 0 plus, right? Because no negative number is the square of anything, but 0 and on up, everything in the reals has a square root. Okay, so there's the image. What's the pre-image there? Well, you can square any number. So pre-image is R, i.e., this function is total. Okay, what about successor? What's the image? So it's the positive numbers, right? The only number not included in the image of suck is 0. Again, this function is total. Okay, what about predecessors? Well, every number is accessible. Right, you can get to 0 by taking either predecessor of 0 or predecessor of 1, and then every other number it's 1 plus the other number. So we have that, and this function is also total. We'll revisit that in a minute, though. Okay, swap. Same story. The image is every number, right? To get to any given number, just choose either the number below it or above it, depending if it's even or odd. And then for the preimage, again, this function is total. Okay, what about a function that isn't total? Well, here's one. Pred prime of n Here's one way to define it. Right, so here we're explicitly saying, okay, this function is undefined when n equals 0. A nicer way to say this might be something like this. Right, I like this one a little better. Pred double prime, because it makes it very clear that, look, we've only defined one of the cases. This is a partial function. Okay, when we talk about a partial function, we'll write something like this. Pred prime and pred double prime are both partial functions from the nats to the nats. So you'll notice what I did here, this is I believe, right harpoon up, so avast Mimedes. And this is used to indicate a partial function, just as a notational note. Okay, let's pop back up. We've defined 4 example functions. We've seen a lot about their parts, talked about their domains and their codomains, which is just basically saying the parts of the type. The domain is the let me write this down actually so it's even in the notes. The domain is the argument type. The codomain is the return type. The preimage, part of domain, we're defined on. And then the image, part of the codomain, we hit. I try to just avoid the word range because for some people range means codomain and for some people it means image, and I just don't want to get involved in that kind of thing. Okay, so we've got the terminology. There's a couple other properties I'd like to show you about. Right? There's 3 in particular. The first is called injectivity, or one-to-one. The next is called surjectivity, or onto. It's hard to read, sorry. And then the last is called bijectivity, or isomorphism. Okay, I'm going to define each of these in turn, and we'll go back and we'll look at the example functions we've talked about and see which of them satisfy these properties. Okay, let's take a look. Injectivity. Okay, we have a function. All of these we're going to talk for the most part about total functions here, just to keep things simple. We have a function f from a to b is injective when for all b, 1, b2 in b, for all b in b, for all a1, a2 in a, f of a1 equals b, and f of a2 equals b, implies a1 equals a2. Okay, so I just stated that a slightly funny way. Here's a simpler way of saying it. For all a1, a2, and a, f of a1 equals f of a2 implies a1 equals a2. Okay, let's look at this pictorially. Here's the set A. Here's the set B. Let's have them both be messy, please. Thank you. We have some function f between them. Okay, and we've got, there's a1, there's a2, here's b. And what we're saying is, what's going on here? Both of these map to the same value, right? To be injective, we need to have it be the case that a1 equals a2. Okay, so in English, f is injective. Let's do it in black. F is injective when no two inputs, when two distinct inputs, let's phrase that a little clearer, when two distinct inputs must have distinct outputs. Nobody shares. Okay, so this is like the 2-year-old's preferred functional property. Okay, so let's, with this in hand, let's go back up and see what each of these functions satisfy or don't satisfy. Okay, injectivity. So what we would need to have for each of these. Let's copy this a little bit. Okay, so which of these are going to satisfy this property? So to be injective, it means there can't be two things that hit the same thing. Okay, but look, -1 squared equals 1 squared equals 1. Okay, so this one is not injective. Successor. Is successor injective? Yeah, the only thing that you'll get, well, it's always going to be 1 greater, so that's the only way to get it. Yes, right? N plus 1 equals m plus 1 implies n equals m. Okay, what about predecessor? Is predecessor, as we've defined it here, injective? I would say no, because look, pred 0 equals pred 1 equals 0. Okay, what about swap? Is swap injective? It is. So for a given number, if it's even, then we'll add 1, and so that's the only number that will hit it. And if it's odd, then we'll subtract 1, and that's the only number that will hit it. Okay, so maybe you can see now the general form that proofs of injectivity will take. You'll either, for a counterexample, find two inputs that gives you the same output, or you'll prove that okay, give me two arbitrary inputs. Let me show you that they necessarily have distinct outputs. Okay, 1 for 3. Let's keep going. Surjectivity. It may help for people who don't have any Latin to know that this is literally throwing in, right? The thing that throws in, and they throw into this to the same spots, and this is meaning throwing on, right? The idea that we're going to cover it. Okay, so what does this mean? F. Oops, let's do it in black. Excuse me. In black, thank you. F from A to B is surjective when, for all B and B, there exists an A and A, f of A equals B. Okay, what does this mean diagrammatically? Okay, this one will do pretty ones. Okay, here's our set A. Here's our set B. That's what F does. So we're saying, give me some B and B. Necessarily, there's some A here that necessarily maps to it. Always. We always hit every B. This is, I think, a little easier to understand than injectivity. It basically says, hey, look, we cover all of B. So to put it another way, the range, or let's not use that word, the image of F is just equal to B. Right? We cover everything there. Okay. Let's look at our earlier functions. What about these for the properties? Okay, can we always hit every real number with square? No. -3? There does not exist an R in the real numbers. R squared equals -3. You need the complex numbers to do that. Okay, surjectivity. Again, no. What about 0? There is no n such that 0 equals 1 plus n. What about predecessor, which is for some reason, it looks like missing part of the letter P. Is it missing it over here? No. Weird. Okay, so for predecessor, yes, absolutely, right? We can hit every possible number, right? You give me a number, I'll tell you how to get there. If it's 0, then there's two ways, either from 0 or from 1. And for any other number, it's just go one higher. So, yep, this one works. Okay, what about swap? Same story. If it's odd, the way you get there is by the even number 1 lower. If it's even, the way you get there is by the odd number 1 higher. So this is also surjective. Okay, we're almost done. One last property. Okay, so bijectivity. Double throwing in my, this is at this point pigeon Latin, double throwing. Right, this is the combination Pizza Hut Taco Bell of properties. F from A to B is bijective when it's both injective and surjective. Right, this is like the centaur. It's like the twofer. It's like the peanut butter and the chocolate and the Reese's peanut butter cup. It's both of the things that you want. Okay, let's do it diagrammatically. Okay, so what's going to happen? A1, A2. Let's zoom in a little so my handwriting is a little bit better zoomed in. A3, A4, and then we've got over here, what do we got? We got some like B1 and some B2 and some B3 and some B4. Okay, and then we need to have some mapping, so I'm just going to map the like numbers just to make my life easier. Right? And so everything here has something in A. That's surjectivity. Oops. And then over on the domain side, everything here maps to something different. Right? That's injectivity. So what this tells us is, okay, for every element of A, F gives us a unique corresponding element of B, and because of surjectivity, we know nothing's missed. So this kind of tells us that there's a one-to-one relationship. I'm going to write this in my rainbow pen because it's such a big deal. Ooh, that's not how you spell that word. There's a 1, no, that's the letter O, man. 1, 2, 1 relationship between A and B. 1-to-1, sort of like there's exact matches. Right, and we'll use this idea to realize that that means A and B in some sense have to be sets of equal size. Okay, so we're not quite there, right? We have really one more video I'm going to do in between to talk a little bit about another important topic. But this is going to be sort of the real money. This is the way that we're going to be able to talk about the sizes of sets, is by defining functions between them. Okay, so we're only 5 videos in, and we're starting to get a glimpse of sort of the roadmap that we're on. Hopefully, if you've been kind of bored by all these properties, you can see that we're going somewhere interesting. We're going to make a minor detour through thinking about function inverses, just like we've thought about relation inverses. And then after that, we'll start talking about sets, cardinality, and countability. And that'll be the main content of what you're seeing on the homework, and you'll be well prepared once you've seen those videos. Okay, I hope everybody's doing well. I hope this video was clear enough. If you have any questions about any of these examples, please feel free to bring it up on Piazza. I did not bother going through the examples for bijectivity because you can answer it for yourself, knowing that bijectivity is just the conjunction of these two properties. So sort of a quiz question for yourself. Which of these 4 functions is bijective? I'll give you a hint. There's only one. Okay, have a good one, everybody.